Welcome to the channel.
In a common source amplifier, the relation between input and output is asked, and also at which node the output voltage is measured. To solve this problem, I am taking example of common source amplifier with resistive load, and from small signal analysis, I am calculating the important parameters like input resistance, output resistance, and gain of the amplifier. Meanwhile, I will explain the operation of MOSFET, and at the end, we are going to conclude the right options from given options. Let's start. I'm drawing this is drain resistor, taking example of n MOSFET, and this is source. Here, common source in the sense the input and output voltage are measured with respect to source. Source is a reference point, source is a ground in this case. This is source terminal, this is grounded. The input voltage is applied at the gate terminal, and output voltage is measured at the drain terminal. And this resistor say as RD. Here we apply the DC voltage, say VDD, and we are connecting it to ground, negative terminal of VDD. The resistor is considered here to measure the current in terms of voltage. So the current is converted into the voltage, and that is the reason RD resistor is considered at drain current. First of all, see the circuit analysis, the effect of RD on output voltage. We are going to apply the KVL. We know that this is battery negative terminal, this is positive terminal. We are going to assign the signs to the resistor like positive, negative, and the output voltage is again positive, negative. So this is the loop. As we are moving from negative to positive, the VDD will be positive. Coming to the resistor, moving from positive to negative. So this will be RD. As I consider the current flowing through this RD is ID. So ID into RD is the voltage drop across RD. Coming to the output voltage, positive to negative. So output voltage is equal to the summation of voltages, which is equal to 0. Now taking V naught term to the one side. So what we are getting? VDD minus RD into ID. What is the effect of change in RD on output voltage? See, as we are going to increase RD, which means that RD ID voltage drop will increase, which is subtracted from VDD, so output voltage will be less. As we are going to reduce RD, the voltage drop will reduce, the difference will increase, and output voltage will increase. Likewise, we are controlling the output voltage, which means that we are controlling the gain of the circuit. Now, we are moving towards the small signal analysis. Why small signal AC analysis is performed in amplifier? The main function of the amplifier is to increase the strength of the signal. So in order to increase the strength of the signal, I mean to say the amplified version of the input and the output, we need to apply small signal, we need to apply small AC signal, and we have to consider some internal parameters to calculate the important factors, I mean to say important parameters like gain and bandwidth. These are two important parameters in the amplifier, and that is the reason we are considering the small signal analysis. While doing this, we are making all DC sources short circuit. In this case, VDD is a DC source, so we are going to short circuit it. And then we are going to draw the small signal model of this circuit. I have drawn the circuit for small signal analysis where VDD is short circuited. So the drain terminal is connected to the source, which is the reference terminal. So let's draw the small signal model. I am considering three terminals. This is gate, this is source, and this is drain. This is the gate terminal of the MOSFET, and we are applying input voltage respect to the source. This is input voltage, and this voltage is nothing but VGS voltage. We know that this is drain terminal, and we are measuring output voltage with respect to source at the drain terminal. We need to consider the current which is flowing through the drain terminal. MOSFET has internal resistance. Small internal resistance means RD, and capital RD, as I mentioned, there is a resistive load. So if you go through the small signal analysis in the sense. So as I consider this is drain terminal, this is RD. We know that the other terminal of RD is connected to the source, that is ground. MOSFET has internal resistor that is nothing but R0. As I say R0, small signal resistor, the internal resistor of MOSFET. And the current flowing through the drain terminal, as I mentioned, this is the drain. So the current direction is downward, that is away from node. So what we are getting in the small signal model of this common source amplifier with resistive load, current source, and two resistors, one internal R0 and one resistor at drain terminal RD. Again, I'm drawing the same circuit with input voltage VGS. This is drain terminal. The current leaving from drain, that is ID. And here I'm considering the parallel combination of R0 and RD. And for simplicity, I'm assigning this value to small rd. This is the resistor, which is combination of R0 parallel to RD. And for simplicity, what I'm taking, that is small rd. And we are going to measure the output voltage at drain terminal with respect to source. So this is V0. Now we are considering the node at drain terminal. This is the node. ID current is leaving from the node. Same way, the current flowing through this. As I say, this is I leaving the node. And as per the KCL, what we are getting, ID plus I, which is equal to 0, which means that the summation of currents leaving the node, which is equal to summation of currents coming to the node. But here we are getting currents which are leaving from the node, and we are taking summation is equal to 0 as per the KCL rule. Now this is ID. We can put the value of I, which is nothing but V0 by small rd. We know that rd is the parallel combination of R0 and capital RD. This is equal to 0. And what about ID? ID is simply nothing but, as per the MOSFET operation, as I'm drawing, this is MOSFET, this is source, which is N, this is drain, which is again N. I'm taking the example of N channel MOSFET. P is the substrate, this is oxide, and what we say, the polysilicon, and this is gate terminal. So if you are going to apply the input voltage, what happens here? If you are going to apply the positive input voltage at gate terminal, in the P substrate, the poles are majority carriers. So what happens? The poles are repelled at the boundary of this oxide and leaving behind the immobile ions. So inversion layer will be formed. The holes are pushed down, leaving behind immobile ions. The inversion layer is formed. And further, if you apply the VDD or VDS voltage here, VDD in the sense VDS voltage here, so this voltage is positive. So this voltage, I mean to say, the drain terminal will attract the electron from the source. So electron flow from source to drain and current direction as per the whole direction. So the current direction will be from drain to the source, and that is the reason what we are taking drain to the source current direction. So this is simply the MOSFET operation. So what happens here, if you apply the gate voltage, the inversion layer is formed and the current will flow as per the VDS application from source to the drain, and that is the reason MOSFET is called as voltage controlled current source. As we are applying the gate voltage, the channel is formed and we can control the channel current as per the gate voltage, and the reason the MOSFET is called as voltage controlled current source. And therefore, the drain current, which is proportional to the VGS voltage or gate voltage, and the value of drain current, this is equal to, we are taking some constant, initially say K, VGS, and this K is nothing but, the value of K is nothing but ID by VGS. As per KVL, R is nothing but the voltage divided by current, and exact opposite here we are getting ID by VL. As per KVL, what we are getting, resistor is equal to V by I, but here what we are getting, ID by VGS. So K is simply nothing but the inverse of resistor, and we say this is transconductance, and transconductance is the ratio of current divided by voltage, and therefore unit of transconductance is ampere per voltage, or in standard form the unit of transconductance is Siemens. So ID value we are considering in this case GM into VGS. So we are going to put this value in the equation. Now I'm going to put the value of ID, which is Gm into VGS plus output voltage divided by RD. RD is the parallel combination of internal resistor R0 and drain resistor capital RD. This is equal to 0. So making denominator same, what we are getting RD into Gm into VGS plus V0 is equal to 0. And therefore taking output voltage to the one side, output voltage which is equal to minus Gm RD Vi. So from equation 1, we are getting the relation between output voltage and input voltage. Negative sign indicates that output voltage is out of phase with input voltage, which means output voltage is 180 degree out of phase with input voltage. Output voltage is inverted version of input voltage. So if I take V out by V input voltage, means VGS is the input voltage. So instead of VGS, what I have written, V input voltage. So output voltage by input voltage is nothing but the gain. What gain we are getting? That is nothing but minus Gm RD. So from equation 1, we are getting the relation between input and output voltage, and from 2, we are getting the gain of this common source amplifier with resistive load. And further we can write the gain which is equal to minus Gm. Instead of RD, we can take internal resistor which is parallel with capital RD, and this is the gain of common source amplifier with resistive load. So from this, the option A and D both are correct. Option A and option D, the output voltage is 180 degree out of phase with input, and we are measuring output at the drain terminal. So option F is the correct for this problem. So this is the solution. Coming to the next, here we can calculate the input resistance, the input voltage that we have to apply to the input of the common source amplifier. When you observe the gate terminal, because we are applying input at the gate terminal with respect to the source, so this is open circuited, and we know that in the open circuit means input resistance is infinity. Now calculating the output resistance. So output resistance, which is nothing but simply the parallel combination of internal resistor R0 and resistor at drain terminal, which is RD. So output resistor, which is the parallel combination of R0 and RD. So ideally, the input resistance should be maximum or infinity, since the input terminal can preserve maximum input to the amplifier, and ideally the output resistor should be less, since there should be no voltage drop, no voltage loss, so that it can drive maximum load. So by observing this, if you go on reducing R0, the gain dependent on R0. So if you reduce this for maximum load, I mean to say to drive the maximum load, the gain will reduce. So in this design, always there is a trade-off between gain and bandwidth. If you go on increasing the output resistance, gain will increase, but bandwidth will decrease. And if you want to increase the bandwidth, we need to decrease R0, but gain will decrease. So always there is a trade-off between gain and bandwidth. So this is all about common source amplifier with resistive load. Thank you.